Hello and welcome back. Today we're talking about masking during inference. This is going to be an advanced tutorial because we're going to be talking about a very nuanced feature of transformers. At the same time, I think that with everything that we've covered off so far in the course, this tutorial should be quite doable, so give it a shot. It's definitely worth it, and understanding things like this about transformers will for sure showcase your deep knowledge on this subject. So for example, if I was interviewing somebody for an advanced position on large language models, this would be like an interview question that I would be asking, whether masking is important during inference and how it plays a role. But having said that, it is an advanced tutorial, so see how you go. All right, so let's have a look. We're talking about inference, and here's our sentence that we're experimenting with. Apples are a type of delicious blank. And we're going to put that into our decoder-only architecture, which is used by large language models. All of these 6 words are going to go through this architecture in parallel and separately. As we discussed, the only time they can reference each other is in this multi-head attention component. Speaking of the multi-head attention components, we've talked about triangle masking. The triangle mask will be applied in this way to this sentence. Now, we talked about this in training. Let's see why it's important in inference as well. We're going to zoom into this part, very end part of the decoder. And this is what it looks like. We've seen this slide before. Basically, that's the decoder. This is the 6 vectors going through. We get these probability distributions and as outputs over here. And these first few probability distributions, or all of the probability distributions except for the last one, are discarded. So the probability distribution from the context-aware vector representation that we get for the word delicious, that one is important to us because that's where we will get the prediction for the next word. So basically we'll look for the word with the highest probability. In this case, it's fruit, and that is the next word. But these other ones, they are byproducts. As we've discussed before, they're byproducts of the way the transformer is set up, of the matrix operations, and they're important during training, but they're not important during inference. They're actually discarded. So that begs the question that if we're discarding these probability distributions, then why are we applying masking during inference? Like, first of all, there's nothing to look ahead at, right? Masking is designed to prevent the transformer from looking ahead. In the case of training, it's important because we're training, we have within segment parallelization, so we're training to predict every single word. That's why the triangle mask is important. But in the case of inference, the word that we want to predict is over here, the word fruit. We're not training anything, and this word anyway doesn't exist yet. The transformer can't look ahead at this word, so there's no point in masking anything anyway because there's nothing to mask. Right, this word doesn't exist yet. So that's the first consideration. We don't have any reason to hide things from the transformer because there's nothing to hide. And the second consideration is, like, why are we applying these matrices if it's a matrix operation after all? And it's, yes, it is fast, but still, why are we using computational resources to calculate to apply the triangular mask? So with 6 words, it's probably not a lot of computation, but imagine if you had 10,000 words. So like if you have 10,000 words in your prompt, you're applying this triangular matrix 10,000 times. What's the point of applying this matrix if it carries no purpose, if it is not useful to us? Can't we just remove that or omit that operation, like switch it off during inference? Right? That's the question that we're answering here. Well, the answer is that this matrix or this step is actually very important, and it's not obvious why. In order to understand why it's important, we have to look at layers. We had a separate tutorial on layers, and as we discussed, what happens in the large language model architecture is first this layer is applied of the decoder, and then instead of going to the linear and softmax over here, the output vectors that we have, they go into this part, into this next layer of the decoder, another decoder. It's a separate layer with its own weights and so on. And then again, and then again, and so on, maybe hundreds of times. And let's look at how the vectors go through these layers. So here we've got our 6 vectors. They go through the first layer in parallel, and they're basically being, we're doing operations, we're getting new vectors, updating vectors, and in the output we have these 6 vectors. And we're not going to turn them into probabilities because that will happen at the end. These 6 vectors are going to be input into the next layer, right? They go as input into the next layer, as input to the next layer after this one, and so on until they get these probability outputs. So why is this triangular masking important? Well, layers is the answer. Let's look at the triangular masking that happens here. Because of triangular masking, let's say, vector number 3. Vector number 3 with triangular masking is not able to take context from vectors 4, 5, and 6. It is only able to take context from vectors 1, 2, and 3. So the vector that we have at the end here, vector 3, it has only context from vectors 1, 2, and 3. So when it comes into here as input and goes to this multi-head attention, vector 3 only has context from vectors 1, 2, and 3, not from no other vectors. So let's say vector 5 will be using vector 3, or let's say vector 6. Vector 6 will be using vector 3 as potentially as for context in itself in this step. So in this step, vector 6 will be using, let's say, hypothetically, it's using vector 3 for context, right? So, but because vector 3 only had context of vectors 1, 2, and 3, that means vector 6 will have context from vector 3, which had context from 1, 2, and 3. So that will be one version of vector 6. And now let's think of another result. Let's say another option. Let's say there is no masking. If there is no masking, then in this case, vector 3 will have context from vectors 1, 2, 3, 4, 5, and 6 from all of the vectors. So when it comes to the end, this vector 3 over here will have context from all 6 of the vectors. And when it comes in here, this vector 3 will have context from all 6 of the vectors. And so vector 6, if it uses vector 3 for context this time, now it will have context from vector 3, which had context from all 6 vectors. And so as a result, we'll have a different vector 6. So as you can see, the result of your like context-aware vector representation in this layer will be different if you have or if you don't have masking here, right? So in one case, vector 6 will look in one way, will look like a certain way. In another case, if you turn masking off, this vector 6 will look in a different, it'll look a certain different way, and so on. And that will keep happening. And so as a result, at the end, vector 6, which is the vector that's important to us, right? So if we go back to our probability distribution, this is the vector that's important to us. So as a result, if you keep masking on, you'll have one version of vector 6 over here at the end, and one set of probability distributions. If you turn masking off, you will have a different vector 6 with different probability distributions because of that. And that's the only difference. But it turns out that that difference is important. Why is that difference important? Well, because of training, because of consistency with training. During training, we know that masking is on all the time because that's how we built this training. So during training, we'll have masking on. And if we want consistency between training and inference, then we have to keep masking on so we get the same vector 6 over here as well in our inference. If we turn masking off, we will get a completely different result, completely different set of probability distributions. Basically, there will be no consistency between training and inference, and the results will be completely different. So it will be like we're training one model, but then we're applying a completely different model architecture. So that's why masking is important during inference. It's a very nuanced way of thinking about, or nuanced feature. It's and it's not obvious. Like, it's definitely not obvious when you only have one layer, when you're looking at the transformer architecture of one layer, because if there's only one layer, then it doesn't matter, because this vector 6 is not going to is getting information is getting context over here. It doesn't care about what these vectors 1, 2, 3, and 4, and 5, how they end up over here, right? It's irrelevant to it. But because there's layers, then in the next layer, so the result of this layer is, for the result of this layer, it's very important whether there is masking here or not. For the result of this layer, it's very important whether there is masking in these previous layers, and so on. And for the result of this layer, it's important to have masking in all of these previous layers. And that's how it works. So if there was only one layer, then masking during inference wouldn't be making a difference. But since there are many layers, masking during inference is important.
Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.